Hi there, my name is Ricardo and I'm here to give you this presentation about best practices in streaming data architectures. I currently live in North Carolina in the United States and I work for this company called Elastic as a developer advocate. I hope you are enjoying the conference, and without further ado, let's get to it. Hello everybody, welcome to the Big Data Conference Europe. I'm glad to be here, and I hope that you are enjoying big time in this amazing conference. And a matter of fact, yes, last year I was in person on Lithuania to participate of this conference, and I have to tell you that that was my fondest memory for speaking at conferences from last year. So it is really an honor to be here again with you, right? So this session is going to be about streaming data architectures. We have a lot to cover, so let's get to it. All right, for those of you that don't know me, my name is Ricardo Ferreira. I work as a developer advocate at Elastic, right? Some of you might know Elastic from the Elastic Stack, Elasticsearch, Kibana, Logstash, and these days Beats as well. And pretty much what I do is developer advocacy and community management, right? I'm part of the community team at Elastic. And before Elastic, I used to work for other companies, other vendors as well, like Confluent, Oracle, and Red Hat. And you often going to see myself like speaking in meetups and conferences about things like streaming data, big data. That's why I'm speaking at this conference specifically, right? As well as some other content like analytics, databases, and cloud. Those are the subjects that I like to speak more often, right? So whatever questions you might have, regardless of this presentation or even after the conference, you can reach out, right? So those are my contacts, my email from Elastic, my email, my personal email. So feel free to reach out. For those of you that know me, I am an open book. Like I don't have too much ceremony. Like just ask your question and I'll try to help, right? And for those of you that use Twitter, please, this is my Twitter handle here. It's going to be available in all the slides. So feel free to follow me as in there as well, right? So I think the best way for us, this session is going to be about discussing best practices for streaming data architectures, right? So that's our goal here today, right? But I think it's important for us to be on the same page about what a streaming data architecture is first, so we can all have the same understanding, and you might be able to observe the best practices better, right, when we do this. So the best way that I found to explain what a streaming data architecture is to explain why it came into play in the first place, right? So if you remember, we used to implement analytics using SQL databases, right? And when I say used to, right, it's kind of a force of the habit of saying, because I'm aware that many of us, right, are still doing this even today, right? So this is not like this is like a 10 years old technology. No, we're talking about we're talking about the culture of how do we implement analytics, right? And pretty much what we do is to have our transactional databases, right, where all the applications go there and do the transactions, insert data, update data, delete data, right? And we're going to have some specialized databases that usually we call data warehouses, right? But sometimes it might have other names. But fundamentally, what this database does is to run all the analytics, right? And in order for this to happen, you need to have some ETL jobs that will continuously move data from this database to another, right? So this is how we used to implement analytics so far. But then we found that this architecture has limitations, right? And when I talk about those limitations, is interesting because sometimes people might argue, what type of limitation are you talking about? This works pretty fine. And indeed, it works pretty fine. Like, I'm not talking about that this architecture doesn't allow you to achieve your goal that you were wanting, which is performing analytics. The problem is we became so used with that architecture that every time we talked about limitations and things that are not necessarily wrong with this architecture, we don't realize that indeed there are something wrong, right? Because I think it became like so rooted in our brains how to do that analytics in that way that we forget to actually criticize the architecture. So TLDR, I mean, in order to be very quick here, I would like to highlight the point that you should not have to be able to move data from one database to another just to perform analytics, right? That's what's something fundamentally wrong with the way we do analytics these days, right? So if you think about it, right, if you have a database that's purely dedicated for online transaction processing, or OLTP, right, it's going to work, right, extremely well, because those technologies, database technologies, are pretty much have been like a designer for this, right? So they scale very well. They can afford any type of use case. They're a general purpose database in the end of the day, right? But by the time you try to combine online analytical processing with OLTP, you're going to see that the database is not going to keep up, right? It's going to eventually slow down. Everything will like start failing, and it will create some user like bad experiences because your queries are going to be slow, and it's going to be a chaos, right? Yeah, and pretty much everybody that worked with SQL database know this, and I don't have to explain this to them in too much detail. They're all gonna, yeah, no, you're right. I mean, yeah, every time we try to bring online analytical processing in terms of SQL databases, things go wrong, right? And for a very long time, we started to think that, okay, this is a limitation of our time, right? But this is just how databases are. But in the end of the day, this is how we learn how to implement analytics. So it is what it is, right? So recently, and by recently, I mean like 5 years, 6 years ago, we have this kind of a huge desire from companies and industries for what we call actionable insights, right? What are actionable insights? Basically, it is the capability of you to move the analytics part, right, as close as possible to when the data happens, right? So if you think about, look at this graph over here, which is a very interesting report that has been created by Forrester. They're called perishable insights, right? This report basically tells you that there is a specific set of windows, like calculated in real time, seconds, or perhaps minutes, right? Sometimes might be minutes, where you're going to implement streaming analytics. But streaming analytics is basically all the analysis, insights, and calculations that you need to do as close as possible when the data happen, right? So this graph, this report tells you that as time passes along, right, like if you increase that window for hours or maybe days or months or perhaps years, right, your ability to find insightful information is going to decrease, perhaps disappear, right? Why? Because you've lost your window of action, right? This is very, very simple. I mean, whatever window of action that you had to take some action, it's already gone. It's past tense, right? So in order you to avoid this, you have to bring the computation part as close as possible for when the data happens. But this is fundamentally impossible if you think about it, that the way we do analytics these days is by moving data from the transaction to the analytics, right? This increase a huge window of time. Like, remember those batch workloads that run every midnight to move data from the business databases and for a data warehouse just because it's outside of business hours? That's your window of opportunity. Things might already have happened at that point, right? So because of this, right, the industry came up with this desire of, okay, we need to have a new architecture style that can address this problem of move the computation part as close to when the data happens. And it's not a very formal naming convention, but we have been calling this streaming data architectures, right? This is an architecture style fundamentally, right? So it is a style, not necessarily a way to go. So there are variations of that style you can implement for your specific use case, but usually you're going to find these 5 typical layers in a streaming data architecture, right? The first layer being the source data, which is the actual data that happens, right? Whatever is being machine generated or human generated, right? And then you're going to have this persona here in the middle called stream storage, right? The stream storage is pretty much the heart of a streaming data architecture because it's where all the data like ends up, right, for storage purposes, right? And in order for this to happen, you need to have a layer called stream ingestion, right? One of the main characteristics of stream ingestion and stream storage is that each one of them cannot become a bottleneck for each other, right? That's the main characteristic. So if you remember the old database ETL days, we would have scenarios where, okay, the ETL process is pretty fast, but then my data warehouse is starting to slow down because of the huge amount of data coming in, right? So this is the type of situation that cannot happen in a stream ingestion and a stream storage layer, right? And in a streaming data architecture, right? So that's something that you should take care of. And then you have this end point here, which is called data analytics, where users are going to is a place where users go to visualize, monitor, and maybe run some insights, run some simulations of data, and all that data came from the stream storage, right? So there are two variations of how that happens, right? Either the data from the data analytics came straight from the stream storage. That's option number one. I would say in my experience that this is the most typical one. People just pass through everything that's from the stream storage to the data analytics, right? Because, hey, data volume is not a problem anymore. So I can just stick whatever amount of data I wanted into data analytics and the users can be happy with it. But sometimes you might have what we used to call in an ETL word data curation, right? Sometimes you have to transform the data, enrich the data, augment the data, right? Curate the data in a form of, all right, maybe the data is wrong, and we have to like decompose it or deconstruct the domain model and build a new one before actually moving to the data analytics. Regardless of the use case, you're going to use something called stream processors for doing this, right? And stream processors share the same characteristics of a stream storage and stream ingestions. It can never become a bottleneck regardless of the data volume, right? And if we're talking about best practice, this is the whole point of this presentation. This is the first one, right? If you ever design an architecture, a streaming data architecture, where each one of those layers are becoming a bottleneck for the previous or the next one layer in the architecture, you're doing something really, really wrong, right? Because it shouldn't, right? So either this is a bad implementation, maybe the technology that you've picked is not very suitable for the use case. So we're going to discuss this in the end, right? Don't worry. I'm going to provide some best practices for you to decide better. But this is one of the red flags that you should be aware when implementing streaming data architectures. Why I'm saying this? Because if you came from the ETL database world, those are concerns that you didn't have. Like, should I pay attention and red flags about performance? Usually not, because this was tolerable in the ETL world, but not here. Remember, the whole point of building streaming data architectures is to move the insight and computation part as close as possible for when the data happens. You're only going to be able to do this if throughout the entire architecture there are no bottlenecks. So keep that in mind. So I brought you here some of the most common technologies, or let's call stacks, that you can use to build streaming data architectures. This is not supposed to be like a finite or like a ultimate guide for whatever stack you should pick. There are a lot of other technologies out there. Those are the ones that I am familiar with, right? That I know, that I've taken a serious look about how that work, and pretty much what type of technologies build up the layers of stream storage, stream processors, and the data analytics. So very fast. And again, this is not supposed to be like a comparison about which one is better, right? Every single one of them works fine, right? I had the opportunity to test most of them, right? And they are beautiful technologies. But obviously, some of them will have characteristics that are inherent. For example, all the cloud providers, AWS, Microsoft Azure, and Google Cloud, right? They have their own stacks for building streaming data architecture. And I've separated here what are the services that build up those stacks that you should be taking a look about considering how to use it, right? This is important because I've seen, for example, right? People from Azure, Microsoft Azure, using Azure SQL database to implement what is considered a stream storage layer, right? Which is wrong, okay? So this is more like a guide for you to decide, okay, what type of technology should I pick in order to implement this, right? And as you can see here, all the cloud providers have a complete stack by their own, right? That means that if you are a user or a customer from that cloud provider, you don't necessarily have to kind of go out and shop around for other stacks or other vendors just to complete your streaming data architecture. So they have everything, which is good, okay? But if you're going to implement using some consolidated technology such as Kafka or Pulsar or Elastic, right? You might have to mix and match, right? Elastic is basically the only option that I know that has pretty much everything that you need for implemented streaming data architectures. It has stream storage, it has stream processors, and has data analytics. Pulsar and Kafka are more like streaming data technologies where you're going to have stream storage. That's the heart of what they do, right? Kafka clusters, Pulsar clusters, and they're going to have, actually, Kafka will have like native stream processor technology, which is Kafka Streams specifically, right? In the world of Pulsar, natively, they have something called Pulsar functions, right? Which is a way for implement stream processor, right? It's good, but it might leave behind some very interesting behaviors that you might need to implement, such as like calculated windowing and buffering and aggregations, right? Those use cases, usually Pulsar is implementing using in conjunction with Apache Flink, which is another project. So that's what I said, that sometimes you're going to mix and match some of the technologies, right, in order to complete your streaming data architecture. Keep that in mind, right? So those might be decisions that you have to take when picking up a new stack for your implementation. All right, let's move forward. This is all about best practice, right? So let's start discussing some of them, right? So I've separated here 7 best practices that there's more than 7, right? Obviously, right? But those are the best practices and concerns that I have observed in customers' implementations in the past that actually dictates a very critical path and ultimately is going to dictate the success or failure of those projects. So that's why I brought this 7 specifically over here, right? The first one is what I call knowing when to draw the line for if I should keep the data on the stream storage layer, or should I keep the data permanently, at least, in the data analytics layer, right? Your ability to draw that line, right, is going to influence and dictate a lot of things, right? Ultimately, it's going to also dictate your ability to actually scale out your streaming data architecture more affordably, cost effectively, and easily, right? So, and this is kind of there's no right or wrong approach here. This is huge depend of what technology you've picked for your streaming storage layer or for your data analytics layer, right? Some of them might allow you to scale out, some of them might not, right? But the point is you have to draw the line, right? And I brought you here some of insightful questions that you should ask yourself about how to draw the line. For example, the first one is, okay, use stream storage every time you are implement a streaming data architecture that has the right once, read many pattern, right? This pattern, just a parenthesis here for those of you that know this pattern, this is a pattern where you're going to store data into a specific location, right? Which is going to act as your single source of truth of your data. And multiple downstream applications are going to potentially, they will be interested on that data and they'll go to that location in order to read. That's what we call write once, read many, right? Why I'm telling you this, because I have seen in the field some people like implement like, okay, I'm going to use a stream storage technology here that basically will have one single downstream application consuming from that stream storage. I would say that, all right, if that's your goal, and that's okay. You have to use stream storage for this. You can't get away from it. But you don't necessarily need to store your data on stream storage. Go to the data analytics layer because there's only one, right? And if the data analytics layer can afford that amount of data that's coming in continuously, right? So you don't necessarily have to store in stream storage, right? You could, but you're going to see that there's another best practice that we are going to discuss called stream storage costs. So this is going to be important if you're suffering for, okay, it's going to be so expensive to keep the data on the stream storage layer. The other one is evaluating if the type of data you're handling is time sensitive, right? Sometimes this is by itself is another best practice we're going to discuss later, but sometimes the concept of time is removed from the stream storage layer because we shape the data sets in such a way to make it the analysis in the downstream data analytics layer easier from the user perspective, right? So we remove this concept of time because the data is deemed as already calculated or shaped in a way they should see it, right? And But sometimes users might have to do some analysis that requires them to have access to the concept of time in the data, right? So this is going to kind of also give you a hint about, okay, if most of the queries that users are doing on the data is time sensitive, right? It might make sense to treat your data analytics as your single source of truths. And using the stream storage, again, you can get rid of the stream storage. They have a role on the architecture for scalability purposes, but you don't necessarily have to have a huge retention period for that type of data, right? Because in the end of the day, you might want to avoid the whole round trip communication between, okay, just because I want to run this analysis again, I have to re-import the data from the stream storage again to the data analytics only for that query. So you don't want to do this because you want to avoid this back and forth of moving data, right? So this is another tip. And I think you should check where is your processing center of gravity, right? This is kind of a very bloated term, but let me explain what that means in reality. This means that in the streaming data architecture that is comprised of about 5 layers, right? You might have developers that would be more comfortable and implement logic that on the stream processors layer, which forces you to keep your data more to the stream storage layer. And you might have developers that will be more familiar with SQL queries or SQL statements or insights analytics that can only be performed on the data analytics layer. So if that's your case, this is going to dictate about your center of gravity, about where your data should be kept, right? So this has to do with your team culture, right? As well as your team knowledge, right? Where most of your developers that do the analytics part are centered, more in the data analytics side or the stream storage side. So this is going to be a hint about, okay, depending of where all the analysis happens more frequently, I should pick one layer or another to actually save my data, to keep my data, right? So another thing very important about streaming data architecture is storage, right? It is interesting because if we evaluate the technologies related to analytics that we have been using for this whole time, right, we might see that there have been a lot of motivation, specifically in the database world, to actually forces you to consume more storage, right? Think about how we used to do analytics in the past, right? We used to have this proliferation of databases throughout the company, right? Because again, a database can only afford so much. And then because of this, the usage of storage within the company would increase accordingly, right? So, in other words, just because you are building a new use case, you might end up having to consume more storage. And some people, aka most people, think that by using streaming data architecture, this won't happen again. So likely this will be a way to avoid the problem of storage expansion. And this is not true, right? Ultimately, you have to worry about storage consumption. And a matter of fact, the phenomenon of every time a new use case comes in, you might end up consuming more storage can happen depending on the technology of your pick, right? This is the interesting part. Depending on the technology you're going to pick, this is going to happen more frequent or not, right? So the first question you should ask yourself, can you control stream storage growth costs, right? So let's give the example of, okay, currently I have 3 use cases implemented on my streaming data architecture. Stream storage is controlled so far, but what if you have to double that? Instead of 3, you have to go to 6. What happens if you triple that, right? So how your storage are going to keep up accordingly? There are technology, Kafka, for example, Kafka and its current state these days, right? All the storage layer is implemented on the broker nodes, right? So that means that in order to increase your storage capacity, you need to bring more nodes, which also brings compute power, which is costly, right? Whereas, for example, Pulsar has a more tiered architecture where they have all the data is in the brokers are basically cached there. They're not permanently stored there. So you have another layer called Bookkeeper, where you can horizontally scale that storage layer without necessarily bringing more compute capacity. So for that point of view, it's more economically easier to grow your storage capacity and keep up with your stream storage growth, right? Same goes for cloud providers. Some cloud providers might charge you for hour of usage, right? So it doesn't matter how many data are you consuming, but you might want to read the underlines of each one of those statements on the rules, because sometimes you might be dealing with a managed service that pretty much everything incur on storage capacity. So you might want to check this, right? And why? Because of the second bullet over here, evaluate data spillage with stream processors, right? This is a very important aspect that you have to check it out. Depending on the streaming processor technology that you've picked, that streaming technology processor might actually incur in an increase of data usage on a streaming storage layer, right? One typical example is Kafka Streams with Kafka, right? In Kafka Streams, when you implement a processing pipeline on Kafka Stream, which is amazing, right? It is an amazing technology, but ultimately, everything that happens on Kafka Streams is going to flush it back into Kafka, right? So it means that depending on the complexity of your Kafka Streams topology or pipeline, you're going to like double or triple the amount of data usage on your Kafka topics, right? I have seen use cases, for example, where people do select everything from a given stream and then replicate this to like 3 different topics just because there are different applications trying to consume that. This is all good, works perfectly, but remember, all the data in Kafka is permanent, so you are increasing your storage costs, right? So you might want to evaluate, for example, okay, instead of using Kafka Streams, I might use Apache Flink, which is all the storage, all the stages on the streaming processing pipeline are handled in a different layer that does not necessarily goes back to Kafka, and then I can evaluate, it's cheaper to scale my storage consumption here on Flink or here on Apache Kafka. Which one is cheaper to grow, right? So this is kind of the analysis that you have to do when you are implementing streaming data architectures as well, right? And of course, you have to evaluate how long the data must be retained, because stream storages, rather if it's Pulsar, Kafka, or anywhere else, you can adjust in a per topic basis the amount of time that you're going to hold that data, right? So this doesn't necessarily have to be forever, right? Forever is going to dictate that. Another aspect that it's a best practice that you should take care very seriously in your implementation is the usage of schemas in your streaming data architecture. I like to say that schemas are contracts for developers, right? And if you use a schema-first approach in your implementation, in other words, if you start leveraging schemas on day one of your implementation, you might avoid some very typical use cases and problems that may rise during your implementation, and ultimately is going to delay the delivery of your first valuable product, right? So the main problem of streaming data architecture is that usually developers like the idea of being schemaless because it grants them a very a free approach to develop their code. But there are consequences on this, right? Every time, like for example, you need to change a downstream processor just because a field was added or removed, right? That might unchain a huge set of changes that might be hard to keep up if you have not only one, but multiple chains in place, right? So try to use schema first as much as possible, right? And using schemas means more automation, right? Just like what happens with database. Like, you remember those design tools and databases where based off on the schemas of a table, you can actually design the relationships between all of them. The same happens with streams, right? If you use schemas, there will be some tools in the market that you could leverage to actually make your life of designing your new data sets, the shape of your derivative streams easier than actually trying to kind of abstract because you have no idea about the shape of your stream, right? So schemas are important, right? And remember, streaming data architectures are extremely distributed architectures. So a change happen in one layer will, and not only may, but will impact the downstream layer in the chain of your architecture. So using schemas is not going to avoid a problem, but it's going to alleviate when you try to implement a fix, right? Because you know what you're doing. Well, my mom used to say, 2 is better than 1, right? So this has to do with something that I actually been observing in the stream storage layer, specifically about why most people try to think that stream storage technologies are so highly available, so highly fault tolerant, that they should not worry about stream storage availability, right? And it is interesting because literally yesterday, I'm not sure how many of you heard about this, but Amazon AWS had a outage in one of these availability zones on East Coast, right? But very close to where I am right now. And a lot of some papers kind of started to call, okay, half of the internet stopped from happening because of that outage, right? Obviously, I'm not talking about this is AWS's fault. Much for the contrary, AWS is doing an amazing job in terms of availability. It happens from time to time, right? The problem is that most of these implementations rely on the service of AWS. It could be any cloud provider. AWS is just an example. Doesn't have a proper DR strategy in place, right? And I have been seeing that most people try to think that, okay, I should not have to worry about stream storage availability because they're extremely high available. So this is a mistake, right? Try to avoid that perception, because just like you would do with databases, your applications, and everything else, you need to provide high availability. You need to work at least with high availability of your stream service. And by the way, you know what service was actually had an outage on AWS yesterday? AWS Kinesis data streams, which is a streaming technology. Which is good, because it means that people are starting to adopting very fast streaming data technologies. But as you can see it, they're not providing very good DR strategies for their implementations, right? So build versus buy, right? Probably this is arguably one of the most typical questions that people come to me and say, hey, Ricardo, what should I do? I should actually deploy my Kafka clusters on my Kubernetes pods, on my own data center, on my own cloud provider, or maybe I should this by using a managed Kubernetes services, or I don't do anything else. I just go and hire a managed service that brings Kafka as a service for me. So build versus buy is by far a very old question, right? This is not necessarily a characteristics of streaming data architectures. We have been discussing build versus buy for pretty much every technology: databases, virtualization, operating systems, development frameworks, IDEs, et cetera, et cetera. So in the streaming data architecture world, wouldn't be different. But I think the first question you should ask yourself is, are you a distributed systems shop, right? This is a very important question, because what I have seen out there is that most developers get so excited with streaming data architecture. It is amazing, right? I am kind of a biased to say that I like pretty much streaming data architecture because they are distributed, and I like distributed architectures. That's what I do for a living, right? And if it was up to me, I would spend my whole day twitching knobs by myself to make sure an architect will be up and running. But the problem is, this is my desire as a developer. You should ask, what's your company's role in this whole idea, right? Are they actually a distributed system shop? Or maybe they're a bank, maybe they're a retail company, which they're not interested necessarily in doing that. So this is usually the friction that you have to evaluate when deciding this kind of things, right? And you should build confidence throughout your entire architecture. This is one of the most common mistakes that I've seen out there, which is maybe remember that streaming data architectures are comprised for 5 layers: source data, stream ingestion, stream storage, stream processors, and data analytics, right? And what I'm seeing out there is that, okay, certain teams are very good. They have very good people for doing the stream storage. They're Kafka experts, they're Pulsar experts, perhaps there are some of the cloud provider services experts, Azure Event Hubs, for example, but they're very, very, very bad in terms of the stream ingestion, right? Maybe they're not even developers, right? They're from the DevOps background. Technically, DevOps background also are developers, but maybe they're not so used to all the best practices for implementing code to ingest data at a high throughput, for example, right? Or perhaps even differently than this, maybe they're from the BI background, so they're very good from doing data analytics, and they have no idea about this whole stream storage, stream ingestion layers, which are typically different from what the data analytics layer is all about, right? So what I'm seeing out there is that they are like building confidence in one specific layer. Like they have very good people for this layer over here, and forget about the everything else, right? For everything else, they just like hire some implementation company to do it, but they're not so confident throughout the entire stack, right? This is a mistake because if you pursue that path, you might end up spending more time building than actually delivering, right? Because you're not experts in all the layers. So you have to build experts in each one of those layers in order to actually build your release cycles with more confidence, right? And also, this has to do with qualification, right? So how costly is to bring someone to implement that architecture, right? This is arguably one of the main problems these days with streaming our data architecture. Professionals that actually are specialized in streaming data architecture are hard to find, right? Kafka experts, Pulsar experts, right? Event hubs experts, or stream processors like Apache Flink, Apache Spark, all those technologies, right? It's very hard for companies to hire them in the first place, and even when they hire, to retain those professionals, right? So you should ask yourself, how costly is to find someone to implement the code, right? So this has to do with the previous bullet, which is build confidence, right? You have to build a team that, first of all, love what they do, right? You have to encourage them that this is important for the company. And you also have to make sure that they're constantly trained, kept up to date with the trends and all of that, right? And this is one of my favorite best practices that I would like to discuss, which is the need, and literally this is a need to understand the technology, right? Probably this is kind of a typical mistake for people coming from the database world, to think that because certain technologies are so similar or close to what they used to have on the database world, they kind of oversee some aspects of the technology, and they don't go deeper in understanding the characteristics of it. For example, let me give you a very good example. Some like Apache Flink, right? Apache Flink is a Java framework on the end of the day, but allows you to implement stream processing code, right? Using SQL statements. So it's very common to see people like, okay, it's very close to SQL. So if I know SQL already, I don't have to worry about the aspects of developing stream processors. No, you should, because stream processors are very complicated technologies, right? There's a bunch. It is a distributed system by nature, right? So the whole CAP theorem might haunt you, right, when you're implementing this. And usually projects fail because people don't fully understand the characteristics of each one of those technologies. A very common question that I have about Kafka streams, for example, is, hey, Ricardo, so how many consumers are going to actually receive the result of a certain stream computation that I'm doing on Kafka stream in my topology? 1, 2, 3, or 4? And in my mind, I think, okay, you should know this answer because it's all Kafka, right? So are you comfortable with the concept of consumer groups, partitions, and all of that? Because this is going to dictate ultimately how many consumers are going to have it. So when you abstract away the certain understanding of the technology, you might actually don't build the actual confidence that you should have in your team, right? Remember the previous conversation, you should build confidence throughout the entire architecture. And you're only going to build confidence if you actually go deeper and understanding the technology, which entails the technology, right? And finally, there's a bunch of people are crazy to understand like performance and streaming data architectures. This is probably because the main characteristics of stream data architecture is performance and scalability, right? But at the same time, they should be more excited and building their own benchmarks, like build their own benchmark in their house, but they keep relying on external public benchmarks that a specific vendor does, the other vendor does, and they just kind of trust blindly that benchmark. Don't do this, right? build your own benchmarks, and have your own opinion about what performance actually means in your environment for your use case. And finally, let's talk about time, right? Time is relative. My friend Albert Einstein said that once, right? And this is really, really true also for the streaming data world, right? Streaming data architecture world. One of the major problems that I'm seeing in implementation of streaming data architectures is that people get confused about, okay, what type of data, what type of time in my data should I actually care about? There are three main types at least. There is creation time, when the data was created. There is ingestion time, when the data ended up on the stream storage layer. And there's processing time, when the data was picked from the stream storage and started to be processing, right? So if you're starting to implement use case that, for example, calculates the top 100 orders from the last hour, so what hours should you consider? Because there might have different timestamps throughout data. So as many as possible, try to set in your generated data a timestamp that represents the creation time, right? And as well as try to replicate that creation time throughout the entire architecture, because even in the data analytics layer, you might need that information in order to like build or evaluate some processing or analysis that you want to build, right? And it is all about time, right? But again, time is relative, because every time the data passes through one layer to another, there's a network, there's latency, that there are hiccups, there are delays that might influence in the concept of time that you might have in a given analysis. So keep that in mind when you're building your generated data. So this is more a concern about stream ingestion and source data layers. And with that, I would like to wrap up this presentation. I think we might have like 2.5 minutes for Q&A. But first of all, I would like to thank you, everybody, for being in this conference and participating of my session. I hope it was constructive. I will be more than glad to answer any questions you might have right now and after on the Ask Me Anything booth. So thank you very much.